Hello everyone, I'm Greg Karlovitz from the Hydrologic Engineering Center. Welcome to our course on statistical methods in hydrology. This video is part 2 of 3 on the topic of exploratory data analysis, and we'll discuss data visualization. Let's get started. Looking at your data is an often skipped step before analysis. Analysts want to get to the numbers, model building, and prediction as fast as they can. However, hidden pitfalls can lie in waiting because numbers don't explain everything. Shown here is a famous dataset called Anscombe's quartet. Each of these 4 scatter plots are obviously different when you look at them. However, if you only looked at the summary statistics, you might think that they're all the same. Each dataset has the same mean for the x and y values, variance for x and y values, the same correlation between x and y, the same best fit regression line, and the same r-squared value for the regression model. If I was presented with these 4 scatter plots, I'd certainly not treat all 4 datasets the same way. However, most of the time, I'm not given scatter plots or any other way of visualizing the data. I get databases or CSV files full of numbers that I have to make sense of. It's easy to fall into the trap of computing summary statistics as a method for learning about the dataset, but it doesn't tell the whole story. Let's talk about a few ways to look at our data to avoid these kinds of issues. A histogram is a technique for viewing univariate data. Multiple histograms can be overlaid to observe the difference between variables if they have the same scale or are properly normalized. The data are discretized into bins, which are usually equally sized intervals of the data. The data are counted by the number that fall within each bin. Histograms are sometimes displayed with raw counts, in other words, the counted number of data within a bin, and sometimes with the frequency, which is the count divided by the total sample size. Coming up with what boundaries to use for the bins can be tricky. There are a multitude of rules, usually based on the underlying sample size, for estimating the bin edge values to use. The default in the R programming language is Sturgis formula, which computes bin sizes using the ceiling of the log base 2 of n plus 1 and is very simple. Sometimes it's a hard optimization problem to make the figure look how you'd expect. The bin sizing is a parameter in the sense that you can change it and your results will change. What this plot shows is 2 important things. One is that the data are positively skewed or right skewed, and that the mode of the data is probably somewhere between 0 and 1. Bins that are too small don't help you see the general shape of the data, like the plot on the left. Bins that are too big overgeneralize the data as well. Finding the right size in between might take a little bit of hand optimization. Kernel density estimates represent the same thing as histograms, except instead of counting the points in discrete bins, it represents each data point as a kernel. Then, for a range of values in the data, it sums up the kernels for each of the data points. Similar to the histogram, the density is sensitive to choice of kernel and a parameter called the bandwidth, which controls the shape of the kernel. These 2 items might be thought of as parameters, but realistically, you still can't go outside the range of your data with this method. Common kernels include the Gaussian, which makes little bell curves, the uniform, also called the boxcar function, the triangular, the parabolic, and so on. For many applications, the Gaussian is perfectly appropriate. This process is much easier to do using something like R or Python than by doing it by hand. So this plot still shows it's the same thing as what our histogram previously showed. It shows a right skew and a mode very close to 0. On the left is a histogram with vertical ticks on the x-axis representing the data observations. On the right is the same data represented using a density plot and Gaussian kernels. Note that the peaks of each of the dashed red bell curves corresponds to a single observation. The bandwidth controls the width of the little red bell curves. To compute the thick blue line, imagine for several values on the x-axis projecting a vertical line through the red dashed lines and adding up all of their values. Computing density plots is far easier with computer tools. Note that the second plot shows evidence of bimodality, which could potentially be challenging for using some kinds of models because most models are unimodal. Recall from earlier that CDF stands for cumulative distribution function. The empirical CDF, or eCDF, is similar to the histogram, except instead of having constant width bins of data and finding the frequency of data in that bin, you have a constant width of probability for each data point. In most cases, this weight is 1 over n, where n is the sample size. There are no parameters in this way of displaying the data, although there is the implicit assumption that each observation has a probability of occurring of 1 over n. What is the cumulative probability of the largest datum in this sample? It's 1. Well, what does this imply? It implies that the probability of exceeding the largest value in the data is 0. What kinds of things can you learn from this plot? Well, we see in this plot that the data are right skewed as previously because there's a long tail out to the right. It also shows that the mode of the data is around 0 because a lot of the data points tend to be clustered close in that area. Recall plotting positions from some of our earlier lessons. Plotting positions are an empirical way of representing data and much in the same way represent the same thing as an eCDF, but there's a few key differences. 1, probability is on the x-axis instead of the y. 2, the probability axis is not linear and it's been stretched or transformed. And 3, the largest value does not have a cumulative probability of 1. Each of the points is associated with an empirical estimate of its frequency, which is only based on the sample size. Anytime you see a plotting position-based plot, or an eCDF, keep in mind that the points have a position on the plot which is defined by the magnitude of the value and some frequency estimated from the sample size. The estimate for frequency only comes from the sample size, so there is a profound amount of uncertainty around the estimate when you get to the far left or right side. And it's sensitive to the way that you compute the plotting position, because there are multiple methods. The plotting position is therefore parameterized in only a weak way. You can't make inferences outside the sample based on the plotting positions well. This plot has an x-axis that has been transformed using the normal distribution, so data drawn from a normal distribution will show up as a straight line. Keep this idea in your back pocket. A normal distribution has a skewness equal to 0. If it shows up as a straight line on the normally transformed plot, what does curvature show? Well, it is an indicator for skewness. Upward curvature, a long left side with values on the right side that curl up like a hockey stick, means positive or right skew. Downward curvature, a long right side with values dropping off drastically on the far left, indicates negative or left skewness. Plotting positions are only estimators for the cumulative probability for the data. They're only based on the rank of the data and the sample size, and attempt to make an appropriate estimate of the cumulative probability based on that. There is substantial uncertainty about the actual exceedance or non-exceedance probability. One model for this uncertainty is based on the beta distribution and can produce limits like this. We will see how to do this in the discussion on extreme value theory. It's also important to note that the value for the data is treated as a constant, but may in real life also be uncertain. These are box plots, also called box and whisker plots. You could start to look at multivariate information with these, with one categorical or discrete variable and one continuous variable. Here's a box plot looking at the effect of one variable on another. The x variable is the direction that the wind is coming from, and the y variable is the maximum 1-hour wind speed for the season being analyzed. Both variables are continuous, but the x variable is discretized into 10-degree groupings. So what does this plot show you? It shows you that the directions with the highest central tendency is in the range of 300 to 340 degrees, but the highest variability is in the range of 170 to 260 degrees, which is shown by wide boxes, long whiskers, and outlier points. Most of the data are highly asymmetrical, with the most being right skewed. Some of them do look left skewed around the north direction between 10 and 40 degrees and 350 and 360 degrees. Well, what doesn't this plot tell you? Well, it doesn't tell you anything about the behavior of the wind direction. This plot doesn't say anything about how often these directions occur. You can use these from univariate data, but they're most often used to visually represent the difference between two or more sample groups. Here is what a box and whisker plot is made of. All of the boundaries of the shape come from the 5-number summary. The thick black band in the center is the sample median. It sits inside the box of the plot, which has endpoints at the first and third quartiles. That makes the width of this box the interquartile range, or IQR. To draw the whiskers, extend a line from the first or third quartile to the last data point that is less than 1.5 times the IQR from the end of the box. The whisker ends at those data points. Any data outside the whisker is plotted as a point and labeled as an outlier. Plotting these in R is very easy with a built-in function. Here is a box plot corresponding to a standard normal distribution. The top of the three plots shows a box plot lined up so that you can see where the box and whiskers would line up in terms of standard deviations. The IQR in this case is a little bit narrower than a plus or minus 1 standard deviation interval. The second plot shows how the regions between the whisker and the box and between the boxes lines up in terms of probability mass underneath the standard normal bell curve. The IQR always has a middle 50% of the data. The distance to the whisker spans quite a bit of data, so in order for a data to be classified as an outlier, it's greater than or less than the 99.65 or 0.35 percentile, which is a pretty rare value. The third plot shows, in the middle, the plus or minus 1 sigma range with about 68% of the data. Outside of that range lives about 16% of the data on either side. The scatter plot is a very popular way to visualize two-dimensional data. It's very simple to plot each pair with a Cartesian XY coordinate and observe what's going on. This plot indicates at least three things. First, large values of the x variable tend to also have large values of the y variable, and small values work the same. Small values are more likely than large values for both the x variable and the y variable. And finally, the scale of the values for the y variable is about an order of magnitude larger than for the x variable. We've used the term correlation a couple of times now, so it deserves a little more formal treatment. We'll see it in further detail during the multivariate analysis discussion. Correlation is a normalized version of covariance. Well, what's covariance then? Covariance is the tendency of a dataset to vary from the mean in the same direction for both x and y values at the same time. It's a multivariate extension of variance, which we've already seen. Correlation measures the same thing, except it scales the result to be on the range -1 to 1. For each value in the dataset, compute the distance from the mean of the x values and divide by the standard deviation of the x values. Then repeat this measurement for the y values. Multiply those two results and add them up for all the data. Take the average of this and you get the correlation coefficient. This measurement really only works for linear relationships, and later on we'll see other ways to measure correlation that are less sensitive to this assumption. Data with no correlation have a value of 0. Data with perfect negative correlation, that is, large values of x always mean small values of y, have a correlation value of -1. Data with perfect positive correlation, where large values of x always mean large values of y, have a correlation value of 1. The 4 plot is a powerful collection of plots for testing assumptions about a data set. The 4 major assumptions that are typically made in an analysis are: data are collected randomly and subsequent observations are not related. The data have a fixed distribution with the same location or central tendency. The fixed distribution also has fixed variation or dispersion. And the data are independent and identically distributed. The first plot is called a run sequence plot. The data are plotted in order, with the x value being the index or order of the data. If the run sequence plot is flat and non-drifting, the fixed location assumption holds. If the run sequence plot has a vertical spread that is about the same over the entire plot, then the fixed variation assumption holds. If there are patterns in the data that make values look related based on the order they were observed, then randomness may be an issue. We have seen time series plots before, and in hydrology we use them all the time. These have the same interpretation as run sequence plots, except instead of the x value being the order the data were observed, it's the date or date and time that they were observed. Here is an example of a run sequence plot that shows good mixing. There are no obvious shifts in the central tendency or the dispersion, and there are no patterns in the data in time. Here are 3 graphs showing the 3 types of problems that a run sequence plot can identify. The upper right shows data that have a time-varying cyclical pattern, which indicates that they are potentially autocorrelated, that is, values close together in time tend to be related. In the lower left is a sample that does not have a constant location or is non-stationary in the mean. There's a transition between 2 periods with different central tendencies. The plot on the lower right has varying dispersion. The data start out with small deviances from the central tendency, and as more observations are gathered, the spread in the values increase. This is also called non-stationarity in the variance. Well, what do you do in each of these cases? If your data are not stationary in the mean, you might need to take one or more subsets of the data, creating periods where the data have the same mean. You might also consider a model which has a variable mean, especially if the observations are successive in time and the mean can be modeled simply. If your data are not stationary in variance, you probably have larger issues. You might consider one or more subsets here as well. Transformation may help, for example, taking the logarithm of the data. A model with variable variance may be possible but can be complicated, as detecting shifts in the variance can be fairly tricky. If your data show autocorrelation, you might not have to do anything, but you'll have to treat your sample as containing less information than just the number of samples it contains. You might also consider explicitly modeling the autocorrelation, such as through a sinusoidal or an AR model, or by modeling the difference between successive observations, which may be independent. Lag plots are created as a plot of each point in the dataset plotted against the next point in order. The first point is plotted as x1 versus x2, the second point is plotted as x2 versus x3, and so on. These plots are shown with a one-to-one line to make it easier to interpret. If the lag plot is structureless, then the randomness assumption holds. The plot here is pretty scattershot, which indicates that a value in the dataset does a poor job of predicting the next value in order. Here are some patterns that you might see in a lag plot. The lower left is still our well-mixed case, which indicates low autocorrelation. The upper right plot starts to cluster along that one-to-one line, which is a sign that the data are potentially autocorrelated. The data in the lower right cluster tightly along the one-to-one line, which is an indication that they are definitely autocorrelated. When you look at that plot, you could see how you might be able to guess its successive values for this dataset by looking at the previous one. This is actually the basis for autoregressive time series models. Histogram shapes should start to point you towards models you might apply to answer questions. Bell curves are nice for when you want to apply the normal distribution, as is the case in many situations. The normal distribution is kind of our null hypothesis for a distribution choice. Unless we have a reason to do something else, the normal distribution often works for what we're trying to do. Short-tailed samples can be harder because there are not many platykurtic distributions in common use. The beta distribution could be useful. Long-tailed distributions arise quite often, but not always in the symmetrical case. For symmetrical and long-tailed, you might consider the t-distribution or maybe even the Cauchy distribution. Asymmetrical and long-tailed is more common, and there are a lot of distributions for that. Skewed distributions come up all the time. Log normal and gamma are two very common cases. This example happens to be the Gumbel distribution, which is useful in extreme value modeling. Bimodal distributions are usually mixtures of multiple distributions, for example, two normal distributions with different means. There aren't many distributions which come out bimodal. The normal QQ plot helps you identify if a dataset might be normally distributed. Normality is an important assumption for several kinds of analyses, most notably linear regression. The normal QQ plot is constructed first by sorting the data, and then by computing the z-score for each data point, which is found by subtracting off the sample mean and dividing by the sample standard deviation. These become the x values for the plot, with the sorted data values on the y-axis. To aid in visualization, a line that passes through the first quartile and third quartile of the data is added. When the values follow the line with no discernible patterns, then the data are likely to be normally distributed. Here are 4 examples of patterns that you might see in a normal QQ plot that indicate non-normality, but also provide information about what is causing the data to be not normally distributed. In the upper left is nonlinearity. Nonlinearity that is either concave up or concave down is usually a mismatch in symmetry. Concave up is more positively skewed, concave down is more negatively skewed than the normal distribution. In the upper right is a sample that is nonlinear but also experiencing bulging below the visualization line. Bulging is usually a symmetry issue as well, but might also be an indicator that the shape of the peak of the distribution is different. In the lower left is an example of data that have shorter or thinner tails than the normal distribution. If the sample quantiles are high on the low end, the lower left, and low on the high end, upper right, it means that the normal distribution expects more observations on the extremes than there are in both cases, and that the sample is short-tailed. The lower right plot has long tails, which are thicker than the normal distribution. If the sample quantiles are low on the low end and high on the high end, It means the normal distribution expects fewer observations on the extremes than there are in both cases, and that the sample is long-tailed. In this video, we discuss data visualization. Two key points to take away from this video are: data visualization can help you avoid pitfalls in your data analysis, and many of the available visualization tools can help you diagnose common issues that might occur in a data set. Thanks, and tune in to the next video in this series on exploratory data analysis to learn about the questions you should ask your data when performing a data analysis.